of Chapter 3. Chapter 3 is a relatively short section. There's only five total sections, but let me go ahead and jump in. So the topic of 3.2 is the idea of logarithmic functions. But I'll tell you what, I can simplify this a little bit. We just got done studying exponential functions, right, like this, in the previous section. And you recall, I mean, you would have some base here raised to the power of some exponent being equal to something. But let me now pose a question. What if you wanted to solve for y? Right? Y equals. Wow, well what could you do? How could you solve for y here? It's an interesting question, because there's no algebra that you can do here. The reason being, it's not an algebraic function, right? So how do we solve for y? Well, we'll return to the idea of inverse functions, inverse operations, right? Because just like if we have an exponential function, we want, or at least we would like to have a way of undoing what operation we've done. Well, the inverse of exponential functions is logarithmic functions. Let me go ahead and there's going to be maybe for some there's going to be some new notation here that maybe you haven't seen before. But I'll go ahead and answer the question. How do we solve for y? Well, this is what we're going to do. Y is equal to, ready? So here's the new notation that you might not be familiar with. The idea of log. And then what's going to happen is the base that we were using for exponential functions is going to go here. And then what's inside the log is going to be x. So logarithmic functions. If you were to force me to use one word, right? If I only had one word to tell someone what is a log, what is a logarithmic function, I would say it's an exponent. Because don't you agree that y is an exponent? And don't you agree that, if you agree with me that log base b of x equals y, it equals an exponent. So this is a way, logarithms become a way for you to solve for variables when your variables are exponents. Now, why might you care? Well, if you had we were talking about the compound interest formulas in the previous section. If you had your credit card statement in the mail, you could use, if you had all the available information, you could use a log to figure out what your interest rate is. If you're dealing with, earthquakes, and you were trying to figure out the magnitude of an earthquake, you would want a log. It's a way for us to solve for variables when those variables are exponents. Okay? So let's talk a little bit about, just a little bit about logs. So definitionally, so what we have to assume that is x is a positive number, right? Or I should say greater than 0, right? And we have to assume that the base is greater than 0 and that the base cannot equal 1. And that's familiar, right? Don't you recall that there were some conditions on the base in the previous section? The base had to be greater than 0. The base could not equal 1. Well, obviously, if this base is going to carry its way to the logarithm, then the same criteria applies. Furthermore, that we saw that those exponential functions were always above the x-axis, weren't they? Right? You never saw it, dip below the x-axis. In other words, what? In other words, your result was always a positive number, right? Okay, now, so assuming that x is greater than 0, assuming the following, then this is how we get to make the statement that base b to the power of y equals x is equivalent to y equaling log base b of x. Now, the base logarithmic function with base b, we're gonna talk about base b just a second. So here's what we're gonna do right now. So this is for many, this is new notation, brand new notation. So what we want to do is let's just practice being able to convert back and forth. So if I give you an exponential function, can you turn it into a log? If I give you a log, can you turn it into an exponential? Okay? Let's go ahead and start. So our goal is we want to change the following logarithmic function back to an exponential function. We want this to look like this. Base b to the power of something equals x. Ready? So I'm going to go ahead and write what we want it to look like. B to the power of y equals x. Okay. Let's go ahead and get started. I will tell you, in the first one will be slightly confusing, for most, and then by the time we get to part C, you're going to say, oh, okay, I got it. This is easy. Ready? So the question is, so we know what we want it to look like. So what in here, what is the base? The 2, the 5, or the x? Which one is the base? Well, you can see it. The base is 5. So how I do this is I'm going to, whatever is here, I'm going to write that first. All right. So I'm going to write this first, the base. Now, it's going to be the base raised to some power. What's left? Well, it's either raised to the power of 2 or it's raised to the power of x. But which one is the exponent? Right? Well, as you can see, as I mentioned, logs are a way of finding exponents. So this is the exponent. So that means 5 to the power of 2 equals what? Well, it's going to equal whatever is inside the log. So it equals x. Done. All right, well, let's go to part B. So remember what I said. Start with the base. Whatever's written here, write that first. And it's going to be base. And we're going to raise that to the power of what? The exponent. Which one's the exponent? It's always what it's equal to. So base to the power of 3 is equal to, well, what's left? What's left is 64. So although you might not have known how to solve this, if I said, hey, can you solve for x? Well, that might have been, you might not have been able to do that, but I tell you, when you rewrote it, I bet you can solve this for x. X is just equal to 5 squared. And if I asked you what was the base in this problem, again, that would be, forgive me, that might be hard to figure out in its current form, but as soon as you rewrite it in exponential form, this is not that bad. Something to the power of 3 is equal to 64. Okay, last one. you remember, hopefully this is starting to get better now. So remember, we'll take that base first. So 3 to the power of, what's the exponent? The exponent is, again, whatever it's equal to. So that's 3 to the power of y. And that's always going to be equal to what's left, what's inside the log. So 7. All right, ready? Now let's go the other way. Now I'm going to give you some questions that look like this, and we're going to see if you can get back to log form. All right, so write each equation in its equivalent log form. So let's turn this into a log. Ready? I'm going to go ahead and write the form that we want. So y equals log base b of x. Okay, here we go. So I would suggest, and again, it's up to you, I would suggest the way you start this is first just write log equals. That is honestly, that is the way I begin each of these, just log equals. And now you know the routine. Let's just figure out where each part goes. So you can imagine I have 1, 2, 3 parts, and we need to figure out what goes where. Let's start with the base. So I have base 12, right? So the base is going to go here. Bear with me for this first problem. I'm going to write it like this. All right, so base is 12. That's going to go right here. So log base 12. All right, and, well, what's the exponent here? Well, don't you agree the exponent is 2? And a log is always equal to an exponent, so the 2 is going here. And finally, what's left is x. All right, ready? I won't use those little boxes this time. So let's agree that start with our base. So base is 3, so that's going to go here. So log base b. The exponent is 3, so it's going to be equal to 3. And finally, what's left is 8. Okay, now I'll go ahead and I'm gonna do this exactly the way I did the previous one. Then I'll make a statement about it. So ready? So in this case, we have base e. So base e goes here. We have the exponent is y, so y goes here, and you know that 9 is what's left, so it's going to go there. So log base e of 9 is equal to y. Now, what I want to state really quickly is I've already mentioned that e is such an incredibly special number, okay? As special as pi, if not, it's up there, right? So it's a very, very special number. But we've already studied how in the previous section, how sometimes e can be used as a base e, right? So what I'm babbling about here is log base e is so important. Okay, it's such an important log that it actually has its own button on the calculator, right? And we refer to this as the natural log. And the button on your calculator, if you want to take a glance, see if you can find it, the button is ln. So if you could find ln on your calculator, normally if you have a TI, it's normally right beside the 4, the number 4, but ln, natural log. All right. So as of right now, you should be fairly comfortable going back and forth. So the next part is how can we use this skill to solve some problems. So we want to evaluate each of these. So log base 2 of 16, how do we do that? How do we do that? Well, we might not, until we've had some more training, we might not yet understand how to evaluate that. But let's just go back to exponential form. Okay, so we're going to go back to exponential form. And then we'll see if we can solve it. Ready? So I've already shown you how to do each of these, going back and forth from exponential to logarithm, exponential. So I'm going to go through this part quickly. So let's get back to exponential. So that would be base 2 raised to the power of. Now, do you see how I don't know what this is equal to, right? And a log is the exponent. So I have no idea what this is equal to. So that becomes our variable. So, okay, so ready? So let's just, let's go ahead and finish this. So this is going to be, we know it's going to be equal to 16, but we don't know what we don't know what the log is equal to, so therefore we don't know what the exponent is equal to. All right, now, at this stage, I bet you could figure out what y is. 2 times 2 times 2 times 2 is 16. So, therefore, y is equal to 4. 2 to the power of 4 is 16. All right, what about the next one? Well, let's go ahead and get it back to exponential form. Well, start with a base, so base 7 raised to the power of, we don't know what that is, so that's going to be y again, has to be equal to 1 over 49. And in case it's been a while, just as you probably know, x to the power of -1 is equal to 1 over x. Now, x to the power of -2 is equal to 1 over x squared. So 7, so we know 7 times 7, right, is 49. So, but this is more than likely it's going to have to be a negative number, correct? Because why? Well, because we have 1 over 49. All right, well, what is it? So y is going to end up being -2. 7 to the power of -2 is 1 over 7 to the power of 2. And, of course, 7 to the power of 2 is 49. Let's keep going. So let's start with our base. So base 25 raised to the power of some exponent has to equal 5. Okay, well, and that just because you know the square root of 25 is 5. And since the square root of x just means, let me change the color here so you know that this is an aside. So, since the square root of x is equal to x to the power of 1/2, well, that should make sense that if 25 raised to the power of 1/2 means the square root of 25. So y is equal to what? Y is equal to, did I write that correctly? Sorry. Make sure I'm writing that correctly. So y must be equal to 1/2. 25 to the power of 1/2 is 5. Okay, last one, piece of advice. So when you have radicals, square roots, cube roots, etc. in your log, turn it back into fractional exponents. So the first thing I'm going to do here is rewrite this. Okay, so that's the equivalent of saying log base 2 to the power of, I'm sorry, log base 2 of 2 to the 1/5. All right, now if it's been a while and if you've forgotten stuff like this, how to go from here to here, you'll have to either reach out to me, or you might have to find some videos online, find some old textbook. But this is just a skill that we need to have. Okay. So now that we have now that we've rewritten it, let's actually answer it. So let's start with the base again. So it's going to be base 2, and it's going to be raised to the power of something, and that's going to equal 2 to the power of 1/5. Well, wait a minute. 2 to the power of something has to equal 2 to the power of 1/5. Don't you agree with me that this is only going to be a true statement if y equals 1/5? Right? 2 to the 1/5 is equal to 2 to the 1/5. 2 to the power of 2 is equal to 2 to the power of 2. Same base, the exponents must be equal. So y is equal to 1/5. Okay, so last bit of material, and then we'll I'll go ahead and take a break. We'll come back for the part B. Let's just make sure we understand, because we're talking about log versus exponential functions. And what we want to do right now is we just want to make sure we have the basic ideas of the domain and the range of each of these. So we'll start with we'll start with the exponential function. Okay, so we're gonna start here, and do me a favor, just look at the blue curve. Okay, that's all we're looking at right now. So what is the domain of this blue exponential function? Well, remember, the domain is what you're allowed to plug in for x. And the good news is, just as you can see, this continues to go forever in this direction. This continues to go forever in this direction. So the domain is all of x. So the domain is from negative infinity to positive infinity. What is the range? Again, please, let's just look at the blue curve. Well, can you agree that this is going to continue to infinity? And it's going to get us really close to 0, but it's never actually going to reach 0. So the range is going to be from 0 to infinity. Okay, well, we've already talked about the y-intercept is always going to be here, 0, 1. The x-intercept, well, if this never ever crosses the x-axis, right? Like a pilot that never ever gets close to the runway but never lands the plane. If this never crosses the x-axis, then there is no x-intercept. Agreed? So b to the x is never going to have an x-intercept. In fact, there is a horizontal asymptote, right? There's actually a horizontal asymptote here at y equals 0. So this will get very close, but will never cross the x-axis. So the horizontal asymptote is at y equals 0. Vertical asymptotes there are no vertical asymptotes anywhere here. So this is just not applicable. Let's now go to logarithmic functions. So I believe I've already made the statement that the log is the inverse of the exponential function. We talked about inverses back in chapter 1. And if you recall, when you have an inverse function, remember the x and the y, just trade places. How's that? So the range of the exponential function is the domain of the log, and the domain of the exponential is the range of the log. And you honestly, you can see that from this. Look at this. We're now looking at this log graph, right? Do you see how this red line never crosses this x-axis? I'm sorry, this y-axis never crosses it, right? So you can't pick x as a negative number. Doesn't work. So that's why the domain is always going to be from 0 to infinity. In fact, if you have your calculator with you, you could try log of a negative number, or try log of 0, and you should get an error. And you're getting an error because, of course, this curve is never going to cross that y-axis. So you're never going to be able to use a negative number for x. All right, and but just as you can imagine, this goes down to negative infinity and continues to rise to positive infinity. So the range, negative infinity to positive infinity. Well, if they're inverse operations, you would, you can x and y swap places. So that's why the x-intercept for your log functions is always going to be at 1, 0. So instead of 0, 1, it'll be at 1, 0. Y-intercepts, well, this is never, just like this never crosses the x-axis, this is never going to cross the y-axis. It gets as close as you want, but it's never going to cross it. So there's no y-intercept. There's no horizontal asymptotes with log functions, right? You don't see these. This just goes on forever, and both. So it's never gonna. You're not gonna worry about a horizontal asymptote, but there is a vertical asymptote, and there's a vertical asymptote right here at the y-axis. It's never gonna cross it. So the vertical asymptote is at x equals 0. Okay, let's go ahead and take a break, and I'll see you in the next video.